You usually expect a massive technological failure to involve some kind of villain.
Right, like a hacker in a dark room.
Yeah, exactly. The whole cyber thriller narrative is just baked into our culture now. You picture this team of state-sponsored hackers typing furiously, breaching a firewall, and pulling the plug on a critical system.
It makes for a great movie for sure.
It does. But, I mean, when you step out of the movies and into the actual landscape of everyday software engineering, you realize the most terrifying outages don't involve an attacker at all.
No, they really don't. The diagnostic landscape we're looking at today is honestly a masterclass in the self-inflicted wound.
Yeah.
It's a system just completely tripping over its own shoelaces while attempting a perfectly normal walk down the street.
Right.
And those are the failures that actually keep engineers awake at night because they reveal fundamental flaws in how we build and trust our own safety mechanisms.
Totally. So, for our mission on this deep dive today, we are opening up a postmortem document from a project called CityLife.
And the premise of this project is just wild.
It genuinely is fascinating. So, to give you some context, someone is building a digital city, but they aren't just coding it line by line themselves. They are building it using a whole fleet of AI agents.
Yeah, these digital workers are actually writing the code.
Right. They write code, they review each other's pull requests, and they ship the logic that runs this city. I mean, they manage a clock, bus schedules, digital wallets. There's an arcade.
It's incredibly complex.
Very. And the agents have their own work lanes, their own queues, and they actually govern each other.
Which is a really compelling look at the future of development, honestly.
Yeah.
But we aren't here to talk about the digital city itself today.
No, we're not.
The failure we are analyzing happened in the board, like the digital workspace or the command center where all of these AI agents plan their tasks and record their progress.
The central nervous system, basically.
Exactly. We are looking at a night where this entire central nervous system just collapsed. And, it wasn't a DDoS attack.
Yeah.
It wasn't a sudden spike in consumer traffic either.
Right.
It was a failure triggered by a single, perfectly well-intentioned request that just wanted to read the rules.
Which brings us to the core theme of this whole deep dive. A system that tells the truth about itself is infinitely more valuable than one that just looks busy.
That is the overarching lesson pulsing through this entire postmortem.
Because this system tried extremely hard to look busy and functional, right? And in doing so, it masked this cascading series of internal catastrophes.
It really did. But before we get to that collapse, we have to look at the peak.
Oh, for sure. We have to look at the phenomenal week this AI fleet was having right up until the exact moment it broke.
And the sources are incredibly generous about this, and for good reason, I think. Before the incident, this project was operating at an astonishing velocity.
The numbers are just crazy. In a 9-day window, the main work board for this AI fleet exploded from 253 items to 585 items.
And it wasn't just planning either. It wasn't just generating tickets to look productive for a dashboard.
Right. The actual completed work skyrocketed. They went from 61 finished items to 271 items in that exact same time frame.
It's a massive jump.
Just to put that throughput in perspective for you, out of 270 entirely new tasks created in that final week, 158 of them were completely finished by the end of it. We are looking at a digital factory running at full tilt.
The throughput is impressive, sure, but if you look closely at the logs, the quality and the rigorous honesty of that output is what really stands out to me.
Yeah, explain that a bit more.
Well, in software, particularly in automated systems, it is dangerously easy to optimize for speed over truth. You can write scripts that just close tickets and report success.
Right, just checking boxes.
Exactly. But this factory was configured to run honestly. Every single one of the 90 completed engineering items in that batch had a tangible link to absolute proof.
I found that detail so striking. It wasn't just an AI agent saying, hey, I did this.
Right. There was a linked merged code change, or a continuous integration test that was verifiably run, or a specific release artifact.
There was no, I'll update the documentation later, just mark it green for the metrics.
Exactly.
Yeah.
Which brings up a really critical standard they had in place. If an item was incorrectly marked complete, say, a fine-off skipped a few implementation steps that were required.
Yeah.
The system didn't just sweep it under the rug.
Or leave it in some kind of vague warning state.
Right. It aggressively rolled that item back to a blocked status.
I have to push back on that a bit, though.
Okay.
Because if they had such an incredibly strict standard for rolling back incomplete work to a blocked status, choosing to make the dashboard look worse, right, to look red, rather than be factually incorrect, why is that kind of radical honesty so rare in the broader tech industry?
That's a great question.
Because it feels almost like a contradiction to see a system this rigorous fail so spectacularly just a few days later.
Well, it's rare because human organizational incentives almost always misalign with system honesty.
Oh, that makes sense.
Think about the pressure in a typical engineering team. You are constantly conditioned to report upward that everything is on track.
Nobody wants to bring the boss bad news.
Exactly. When a dashboard shows a bright red block status, it invites immediate and often uncomfortable scrutiny from management. So, over time, teams subconsciously design workarounds.
Right, they create soft statuses.
Yeah, or they allow technical debt to be categorized as done for now, all just to keep the lights looking green on the executive report.
But this AI fleet didn't have that psychological baggage.
Exactly. It was programmed to prioritize the verifiable state of the system over the optics of productivity.
And they were tackling real complex infrastructure work with that rigorous standard. Like they pushed a full password change and recovery flow all the way to real users end to end.
Which is not trivial.
No. And they caught and fixed two distinct classes of broken builds. These were tests that were silently passing while verifying absolutely nothing, which is a total nightmare to hunt down.
Oh, silent passes are the worst.
Yeah. They repaired lost parent plan links. They made build machines restart proof. I mean, by every available metric, this was the fleet's absolute best week.
Which is exactly what makes the sudden freeze so jarring. Because fragility often hides behind periods of high success.
You assume everything is fine because it's moving fast.
Right. When a system is flying that fast, you assume the foundation is rock solid. But velocity can easily outpace resilience.
Which brings us to the moment the illusion shattered.
The freeze.
Right. So the human operator of this project sits down, wanting to check on this massive surge of progress, right? And they attempt to open the digital workboard. Just a simple browser request to load the page.
And the screen says loading. And it just stays there.
It just sits there.
For 114 seconds.
I want you to really think about 114 seconds of hanging in a modern web browser.
It's an eternity.
It is an absolute eternity. You aren't just waiting. You're actively wondering if your local internet went down. You're checking your router lights.
Yeah, exactly.
The main view hummed for nearly 2 minutes. The roadmap view spun for 58 seconds and just never finished. It locked up the browser's internal rendering threads so aggressively that their automated interaction tools completely timed out and died waiting for it to paint the screen.
And this exposes the first massive architectural blind spot of the deep dive. When you dig into why the browser hung for 114 seconds instead of, failing gracefully, you've hit a concept that sounds trivial, but is devastating at scale.
Missing timeouts.
Missing timeouts.
Yeah.
The page had no deadline configured for its network requests.
It's wild to me that they missed something as fundamental as a request timeout.
Right.
Like for anyone who isn't a developer, when your application asks a server for data, you don't just leave the connection open indefinitely. You say, I need this data and I will wait exactly 5 seconds. If you don't answer, I'm severing the connection and throwing an error.
That's how it's supposed to work.
But this page essentially told the server, I will wait for you until the end of time.
And that's the exact mechanism of the failure. Because there was no timeout, there was no trigger to admit failure. And here's the really tragic irony of that missing configuration.
Oh, I know what you're going to say.
The system actually had a beautifully designed fallback plan. They had engineered a really robust safety net.
Right. They had a locally stored offline cache of the board data.
Exactly.
And the entire purpose of that cache was to act as a degraded state. So if the live server catches fire, the web page is supposed to detect the crash, intercept the failure, and instantly load the cached data.
Which is brilliant in theory.
Yeah. You might be looking at information that's 5 minutes old, but you aren't staring at a white screen for 2 minutes wondering what happened.
But that safety net code was rendered completely unreachable.
Because it never failed.
Right. Because a fallback mechanism triggers on a failure event like an HTTP 500 error, a connection refusal, or a discrete timeout exception. But a request that hangs infinitely never formally fails.
It just exists in a permanent state of pending.
Yes. So the web page is just holding its breath, thinking, any millisecond now, the data is going to arrive.
And because it never admits defeat, the safety net is never deployed. It's like having a reserve parachute that only deploys if you explicitly shout that you're falling, but you've passed out from the altitude.
That is a perfect analogy. And it highlights why you don't add deadlines just to make a system feel snappy to the user. You add timeouts to force a system to tell you the truth about its health.
That goes right back to the theme.
Exactly. A deadline turns a mysterious, unresolvable, frozen state into a highly actionable, degraded state where you can say, I'm broken, but I can tell you exactly why. Without a boundary on that wait time, you don't have a resilient system. You just have a system that is incredibly patient while it slowly dies.
But the hanging browser is just the symptom, right? The screen is frozen because it's waiting on a server that has gone completely silent, which forces us to look under the hood at the platform itself. What was the server actually doing during those 114 seconds?
Well, to understand the server-side failure, we have to look at how they configured their redundancy.
Okay, let's break that down.
So in any serious deployment, you don't just run one instance of a critical service. You run identical copies, replicas. If replica A gets overwhelmed, replica B is sitting right there in the pool to take over.
The classic load balancing setup.
Right. But here's where the logs show something deeply strange. They had two identical copies running, but one of them was completely, unequivocally dead.
Not just sluggish.
No, not dropping a few packets. A total corpse.
It was entirely unresponsive. But its twin, the other replica sitting right next to it in the exact same network block, was performing phenomenally well. It was cheerfully answering the exact same data requests in a blazing 13 milliseconds.
13 milliseconds is virtually instantaneous.
So if you have a routing platform managing these two copies, why wouldn't it just instantly divert all the traffic to the healthy 13 millisecond replica?
Because the platform was completely blind to the fact that the first copy was dead.
How is that possible?
Because the engineering team never configured a health check.
Oh, man. So it's essentially a restaurant with two chefs on the line.
Right.
Chef A is a prodigy, plating dishes in seconds. Chef B has passed out cold on the floor. But the expediter managing the tickets never actually looks into the kitchen.
They're just handing them out blind.
Exactly. They just blindly use round-robin routing, handing one ticket to the genius and the next ticket to the unconscious guy. And half the restaurant is just starving in the dining room.
That analogy maps perfectly to the network behavior here. The platform manages traffic by periodically tapping each replica on the shoulder and asking, are you healthy?
Which is usually just a simple ping, right?
Yeah, a simple ping to a specific route that returns a 200 OK status. If the replica doesn't answer, the platform pulls it out of the rotation. But if you leave the health check configuration fields entirely empty in your setup files, the platform defaults to a terrifying assumption.
Which is?
If the process hasn't completely exited at the operating system level, it must be healthy.
Wow. Which is how you end up with 9 out of 12 requests failing at the worst point of this outage. And we aren't talking about massive data pipelines here either. The requests that were timing out were for the smallest, simplest pieces of data in the system payloads of just a few hundred bytes.
It completely shatters the illusion of safety that comes with simple duplication.
It really does.
There is a pervasive myth in engineering that simply having a second copy of a service gives you high availability. Unmonitored redundancy isn't redundancy.
I feel like engineers would argue that technically the math says you have a fallback.
You have a fallback in theory. But in practice, if you aren't actively and aggressively verifying that both copies can process work, you haven't doubled your reliability.
Yeah.
You have maintained the exact same level of unreliability, but you've doubled the surface area for failure.
Right.
The only thing you've added is a comforting narrative. You sleep well thinking, hey, we have replicas, when the reality is your dead backup is actively acting as a black hole, silently eating half your production traffic.
A comforting narrative instead of verifiable truth. It loops right back to the central theme again. The system assumed the server was fine because it didn't force it to prove it was fine.
Exactly.
But this still leaves the biggest mystery of the night. We have a web page that won't hang up, and we have a platform blindly sending traffic to a corpse. What actually killed that replica in the first place?
If you trace the architecture back to the root spark, you find a feature that was built with the best of intentions.
It was a reporting feature, an audit tool.
Right.
And an audit tool makes perfect sense. I mean, we just spent the beginning of this deep dive praising the system for its rigorous honesty and its insistence on linking every completed item to verifiable proof. An audit tool is just the logical extension of that philosophy.
It really is.
It was designed to ask, show me exactly what has been delivered across the entire fleet.
And it was designed safely, too, or at least so they thought. It was strictly read-only, meaning a bug in the query couldn't accidentally delete production tables or corrupt the state of the database.
Right.
It was locked down behind administrative privileges. It seemed entirely benign.
But the fatal flaw was in the scope of the question it asked. To build this comprehensive audit report, the feature was programmed to load data, but it didn't load it iteratively. It didn't paginate.
No, it loaded everything.
Everything. Every single work item on the board and every single piece of complex nested evidence attached to every single item simultaneously.
It pulled the entire history and state of the digital city into active memory all at once. And in distributed systems, memory is a hard physical ceiling.
Right, it's not infinite.
Think of a web service's memory allocation like the surface area of a desk. You can only juggle so many open files at one time. If you bring over one project folder, process it, and put it away, the desk remains clear.
But if you back a dump truck up to the desk and unload the entire corporate archive at once, the desk snaps in half.
Exactly. And the source notes that before this audit was even requested, this specific service was already sitting at 96% memory capacity.
96%.
It was running incredibly hot, just maintaining the baseline operations of the AI fleet. The desk was already covered to the edges.
So if we walk through the minute-by-minute logs of the collapse, it's chilling how fast it happens.
It really is a cascade.
The administrator clicks a button to run this innocent read-only audit. The request hits the server tries to allocate the memory to hold this massive, unbounded list of items.
And the memory ceiling is breached almost instantly. The first cascading failure is the database connection. The ORM, the tool that translates code into database queries, is trying to deserialize millions of bytes of data, and the runtime environment just chokes.
The connection dies right in the middle of reading the stream.
Right, so the query fails, but the server itself is mortally wounded by the attempt. The garbage collector in the runtime is likely panicking, trying to free up memory, which spikes the CPU, causing regular request handling to freeze.
And then 6 minutes later, the service just gives up.
It drops out of the registry entirely.
It stops answering network pings. It formally becomes the dead copy we were just talking about.
It's exactly.
And this is the most crucial admission in the entire postmortem. It wasn't an external attack. The team's own audit triggered the outage.
Yeah.
A single read-only query run exactly once by a review process looking for problems took down half the capacity of the entire system.
And the contrast with the surviving replica is what proves the root cause.
Right, the twin.
The twin copy, the 13-millisecond one that didn't receive the audit request, recorded absolutely zero problems, zero latency spikes, zero memory alerts during that exact same time window.
I really appreciate that the authors of this postmortem didn't try to bury this as a random memory leak. They highlight it as the primary finding. Because if one ordinary read request from an admin panel can assassinate a primary service, the system was never structurally safe.
That is a bitter pill for many engineering teams to swallow. If your system is hovering at 96% utilization and it only survives because nobody happens to click the export all button very often, you haven't engineered a resilient architecture. You have just been lucky.
And as the source document so brilliantly distills it, luck is not a safety mechanism.
Luck is not a safety mechanism. It forces you to look at your near misses not as successes, but as unexploded ordnance.
I feel like you could build an entire engineering culture around that one sentence. But the outage doesn't stop at the dead replica. There's a second highly specific detail in this architecture that elevates this from a standard "we ran out of RAM" incident into a profound lesson on blast radius.
Yes, and it involves the AI agents themselves.
Right. Let's talk about the collateral damage.
So this is where we see the fallout of a poorly isolated architecture. The AI bots the agents actively writing code, reviewing pull requests, and making logical decisions rely on a specific communication layer to talk to their language models. That communication layer is essentially the brainstem of the fleet.
And where did that vital cognitive layer live?
In the exact same memory space as this massive heavy lifting reporting feature.
They shared the same physical memory allocation. They shared the same desk.
They did.
Now, I want to focus on why engineers build monoliths like this, because it isn't always out of stupidity. In the early days of a project, putting all your software in one big box is highly efficient.
Oh, absolutely. You don't have to deal with network latency between microservices. You don't have to manage complex authentication between internal tools. It's fast to develop.
It is entirely rational during the prototyping phase. But as the system scales, that shared memory space becomes a massive vulnerability.
Because when the reporting feature asked for everything and the memory spiked, it didn't just crash the report. It starved the surrounding processes.
It suffocated the AI agents.
Right. The logs show that when the audit tool sucked up all the available memory, 2 out of 8 of those crucial calls to the AI models failed outright.
The agents literally lost their ability to process thought because a neighboring thread ate all the resources.
It is a devastating architectural flaw. The source phrases the lesson perfectly. The plan and the thinking should never have been able to reach into the same pocket.
It's poetic in a dark way. A request to simply read the historical plan took away the active fleet's ability to think.
It's a failure to separate the control plane from the data plane, or in this case, the reporting plane from the operational plane.
Which is so common.
Yeah. If you have a heavy, unbounded administrative tool, it absolutely must be isolated in its own dedicated memory space on its own infrastructure. If someone runs a terrible query and crashes the reporting tool, the only thing that should happen is that reports become unavailable.
Right. It should never be physically capable of reaching over and suffocating the core operational logic of your entire fleet. It's like asking someone to sprint a marathon while simultaneously forcing them to recite the encyclopedia from memory. They don't just fail at reciting, their heart gives out and they collapse on the track.
Which brings us to the ultimate fix for the root cause. You can add timeouts, you can fix your health checks, you can isolate your memory pools, but none of that solves the original sin of the query itself.
The golden rule introduced here is brutally simple. Never read all.
Never read all. It's not buy more memory. It's not optimize the database indexes so we can read all faster. The durable solution is to fundamentally change how the software asks for data.
Ask for exactly what you need to display on the screen and force the other end of the connection to summarize it.
Exactly.
Let's talk about the staggering inefficiency that was happening here, because the math behind this unbounded query is just mind-boggling. We're talking about a board with 585 total items on it.
Right, 585 items. To render 585 items on a web browser properly, meaning you were only asking the server for the text titles, the current status, and the essential metadata needed for the display requires roughly 15,000 bytes of data over the network.
15,000 bytes. In the modern era, that is virtually nothing. It's a fraction of a megabyte. It should load in the blink of an eye on a 3G connection.
But because the interface was coded to ask for everything, the object relational mapper on the server eagerly traversed every single relationship.
Oh, no.
It pulled the item, then it pulled the massive blocks of evidence attached to the item, the historical logs, the full text of the code reviews. It packaged all of that up and sent it down the wire. The system was generating and downloading about 1.5 million bytes every single time that endpoint was hit.
So 15,000 bytes versus 1.5 million bytes. That is 100 times more data than was actually required to draw the exact same picture on the user screen.
100 times more memory allocated, 100 times more network bandwidth consumed, 100 times more serialization overhead on the CPU.
That is just wild.
And this wasn't a one-off batch job running at midnight either. It was doing this on every page load, every time a user hit refresh.
Every time an AI agent updated a status, the interface would blindly request the entire 1.5 million byte payload from scratch.
And the most frustrating detail in the postmortem is that the capability to be efficient already existed in the backend.
Right. The server was fully programmed to accept precise commands. You could pass parameters saying, only show me items in the testing lane or only return the titles.
The capability was there, but the client code just never bothered to ask. It relied on a lazy, unbounded fetch-all pattern that worked fine when the city had 10 items in it, but became a lethal weapon when the city grew to 500.
But this is where the plot thickens, because this wasn't an isolated mistake by a junior developer on a Friday afternoon. The sources reveal a systemic pattern of this exact behavior across the architecture.
It wasn't an isolated incident at all. The same shape of mistake, the unbounded list query, caused 2 other distinct outages in that exact same month.
One was another web interface that hung completely because it tried to load every single item in the entire database into memory just to filter them locally and show a handful on the screen.
And the other was even worse, honestly. It was a scheduled automated background job. It was quietly waking up every 10 seconds, loading the entire directory of AI agents into memory, doing nothing of value and going back to sleep.
Every 10 seconds.
Every 10 seconds.
Right.
Forever.
A nervous tick that is slowly eroding the foundation of the server. So when you see the exact same architectural anti-pattern bring down a system 3 times in a month, written by engineers who absolutely know how to write a paginated query, what is the actual solution?
Well, putting a note in the Slack channel saying, hey guys, be careful with large queries, isn't moving the needle.
Definitely not.
Telling engineers to be careful is not an engineering strategy. It's a wish. If you want to change systemic behavior, you have to implement rules that physically prevent bad code from reaching the server. You have to fail the build.
Let's dive into what that means in a modern continuous integration pipeline. For anyone not deep in DevOps, think of the build as the automated assembly line that takes an engineer's raw code, packages it, tests it, and prepares it for deployment.
Right. And a build check or a lint rule is like a highly aggressive automated inspector on that assembly line. Imagine writing an email and your spell checker doesn't just put a squiggly red line under a typo.
Yeah.
Imagine it physically disables your send button until you fix it.
It refuses to let you push a known mistake into production.
Exactly.
Yeah.
The source document dictates that they needed to write explicit rules into their pipeline that scan the code for unbounded list fetches on live request paths. If an engineer writes a query that does not include a hard maximum limit, a pagination cap, the build fails. The code is rejected.
They also discussed implementing size budgets. If an endpoint is tested and the response payload balloons past a certain kilobyte threshold, it trips an alarm and breaks the pipeline in the safety of a testing environment rather than waiting to crash the production server.
And tying it back to the 114-second freeze, you add a lint rule that absolutely forbids any network call from being merged into the code base unless it has an explicit timeout value attached to it.
Now, I can hear lead engineers listening to this and breaking out in a cold sweat.
Oh, I'm sure.
Because if you have a legacy code base, and let's be real, any code older than 3 months feels like legacy code. You probably have hundreds of these unbounded queries hiding in the dark corners of your app.
You definitely do.
If you turn on a strict rule tomorrow that breaks the build for any unbounded list, you paralyze your entire engineering team. No one will be able to ship a single feature or bug fix because the pipeline will be perpetually broken by old sins.
That is the pragmatic reality of dealing with technical debt. You can't just halt all business operations for 6 months to refactor every old query. But the source document provides a brilliant, highly actionable strategy for this exact scenario.
The exception list.
Yes, you implement the rule, but you grandfather in the legacy mistakes.
How does that work in practice?
You run the strict check across your entire code base once in a diagnostic mode. You identify the 300 places where the code currently violates the new never read all rule. You take those 300 specific file paths and put them on an explicit exception list, like an ignore file.
Ah, so you tell the automated inspector, look, we know these 300 spots are terrible, let them pass for now.
Exactly. You stop the bleeding immediately. The new rule is enforced on every new line of code written from today forward.
Yeah.
No engineer can introduce a new unbounded query. And the crucial mechanism for the exception list is this. The list is allowed to shrink, but it is physically prevented from ever growing.
That is brilliant. As developers naturally touch those older files to add features or fix unrelated bugs, they are forced to fix the unbounded queries while they're in there.
Yep.
They remove the exception, the list shrinks, and over time, the system heals itself without ever halting product momentum.
You don't demand perfection overnight. You just demand that the system stops getting worse today.
Okay, we've covered the memory exhaustion, the shared brainstem, the missing timeouts, and the strict rules required to enforce boundaries. But as we move toward the aftermath of this incident, we hit a deeply human phenomenon.
Escape.
We hit the psychological need to find a scapegoat. And in complex systems, that scapegoat is almost always the database.
It is a fascinating pivot in the postmortem because it perfectly captures the engineering desire for a massive structural excuse. When a system collapses and ruins everyone's evening, it is deeply embarrassing to admit that the root cause was a missing 5-minute health check and a lazy query.
Nobody wants to write that executive summary.
Exactly. So the satisfying narrative that quickly circulated was, we chose the wrong database technology. The database is unstable. We need to migrate.
Blaming the database is the ultimate get-out-of-jail-free card. It's a huge, complex piece of external infrastructure. If the database is fundamentally flawed, it absolves the application developers of responsibility. It turns a careless coding error into a strategic architectural mismatch.
But the author of this postmortem refuses to let that satisfying lie take hold. They systematically exonerate the database using hard telemetry.
Let's look at the actual measurements. First of all, the sheer volume of data we are talking about. When people say the database couldn't handle the load, you assume they're processing terabytes of transactions.
The entire body of data in question, the complete state of the board and all its historical evidence, was under 6 megabytes in total size.
6 megabytes is a single uncompressed photo on a modern smartphone is larger than the entire data set this system was trying to manage. That is microscopic. You could hold that entire database in the cache of a modern CPU.
The database wasn't struggling, it was practically asleep. The telemetry showed it sitting completely idle, utilizing a barely measurable fraction of a single processor core.
But what about the complexity of the queries? Maybe they were doing insane multi-table joins that locked up the engine?
That's the other irony here. The database they had selected was a highly advanced graph-style database, specifically engineered for traversing incredibly complex, deeply nested relationships between diverse data points.
So it was a Ferrari.
It was a Ferrari. But out of all the queries the application sent to it during this incident, not a single one actually utilized those advanced traversal features. The application was basically using it as a dumb key-value store, asking for flat lists of items.
They were driving the Ferrari 5 miles an hour down the driveway to check the mail, and then blaming the transmission when they drove it into a ditch.
You could certainly argue it was the wrong tool for the job, simply because it was vastly over-engineered for what they were doing. But that architectural mismatch had absolutely zero causal relationship to the outage.
I have to ask about a specific number in the report, though, because I can see why the team latched onto it. The dashboard showed that the database had restarted 17 times.
Yeah, that looks bad.
17 restarts looks like a spectacularly unstable piece of infrastructure. If I saw that, I'd scream migrate too.
It looks alarming until you apply basic critical thinking and check the surrounding infrastructure logs. The database process itself didn't crash 17 times due to internal errors.
So what happened?
There was a single underlying machine reboot at the operating system level, a piece of shared hardware reset. That one single event forcefully terminated 27 different processes simultaneously, all throwing the exact same sudden death error signature.
So it wasn't the database failing, it was the floor falling out from underneath it.
Exactly. It's like a rolling blackout hitting a neighborhood. 27 houses lose power at the exact same second. The database was just one of the houses on the street. It was a victim of an infrastructure event, not the cause of an instability event.
But the dashboard blindly aggregates restart count.
Right, and human nature takes the most alarming number and builds a narrative around it.
If the leadership had believed that satisfying lie, the consequences would have been massive.
They would have greenlit a database migration.
Which is easily a 6-month engineering nightmare. You have to rewrite every query, migrate the schema, run dual writes, plan a massive cutover. It costs hundreds of thousands of dollars in engineering time. And at the end of that 6 months, they would launch the shiny new database.
Wait, let me rephrase. They would launch the new database
And the exact same outage would happen the very next day.
Yep.
Because the new database would still perfectly execute the unbounded query, load 1.5 million bytes, send it to a memory space that was 96% full and crash the server, which still wouldn't have a timeout or a health check. When a system breaks, the first plausible villain is usually the one that's easiest to blame, not the one that actually pulled the trigger. It takes immense discipline to ignore the satisfying story and dig down to the mundane truth of a missing configuration field.
It really does. And that commitment to mundane truth brings us to the final and, frankly, most profound revelation in this entire document. As we pivot away from the software architecture, we find a flaw in the organizational architecture that dwarfs everything we've talked about so far.
We have to go all the way back to the beginning of the story, the very good week, the explosive throughput. 271 items completed, 158 brand new tasks finished in days.
With all that incredible verified velocity, you would naturally assume that the team was aggressively churning through their backlog. You would expect that the extensive list of urgent cleanups and structural problems identified in their previous review cycles had been systematically demolished.
But the reality recorded on the board was completely inverted. Almost none of that historical problem list had been touched. The queue of unsorted incoming work hadn't shrunk, it had actually grown slightly.
Not a single item in the incoming queue had been processed since the day it was created. Long-running tasks that were marked in progress had all quietly stalled out and died.
And the most glaring failure of all, the priority logic was completely upside down. Items that the team had explicitly marked as the absolute most urgent restorations in the entire ecosystem were scheduled to be picked up last, entirely because of a flaw in how the ordering system parsed the queue.
So you have a highly advanced AI fleet, capable of incredible execution, furiously manufacturing low-priority widgets, while the actual critical infrastructure rots in a queue. Why?
Was the AI hitting a cognitive limit? Was the system out of resources?
It wasn't a lack of computing power. It wasn't a resource constraint. It was entirely caused by one single human bottleneck.
One approval.
A single review item sat in a required status waiting for a human decision. It sat untouched for 9.5 days.
9.5 days.
And because of the rigid sequential rules written into the governance system, every single one of those urgent cleanups, all the critical restorations, were formally stacked behind it in the queue, unable to proceed.
It's the ultimate traffic jam. You have a multi-lane, high-speed autonomous highway, and it is completely brought to a standstill because one single car is parked sideways in the only toll booth, and the driver went on vacation.
That is exactly what happened. While the AI agents were busy generating and instantly completing hundreds of brand new, lower priority tasks that didn't require that specific approval lane, the entire critical cleanup list remained frozen. Byte for byte, the database showed those records utterly unchanged for over a week.
And when you look closely at what was actually stuck in that traffic jam, it gets even more maddening. The sources detail that 5 of those blocked items were entirely finished. The code was written by the agents. The continuous integration tests were run and passed.
The changes were successfully merged.
The logic was deployed to the environment. Technically speaking, the engineering work was 100% complete.
So what were they waiting for?
They were waiting for a human being to look at the screen, acknowledge the verified proof, and officially click a button that said, "Yes, I agree, this is done."
A physical action that is estimated to take maybe 5 minutes of human attention.
And they waited for that 5-minute confirmation for a full week.
The Postmortem author describes this dynamic as a ghost town of governance. And I think that is one of the most powerful concepts in this entire deep dive.
Unpack what a ghost town of governance actually looks like.
Well, this system was meticulously designed to appear governed. Every transition had a gate. Every completion required attached evidence. No AI agent was permitted to autonomously promote its own work. It required an independent review step. The architecture was obsessed with the aesthetic of rigorous oversight.
But it was just an aesthetic.
Entirely. Because when you audited the actual records to see who was providing this oversight, there was nothing there. Not a single entry in the system showed a human decision-maker taking action.
All the detailed notes on the board, all the status transitions, the detailed comments, they were all generated and written by automated bot accounts talking to each other.
So if the bots are doing all the paperwork, but the system is stalled waiting for human approval, where were the humans actually making decisions?
They were making them out loud, in verbal conversations, in stand-up meetings, on quick video calls throughout the week. The humans were talking to each other, verbally agreeing on what needed to happen, what was a priority, and then they simply never recorded those decisions in the digital system.
None of the crucial human authority that actually drove the project was recoverable from the digital record.
It's a complete facade. It looks like a perfectly managed automated workflow, but it is structurally hollow.
The fundamental takeaway here applies to any organization, software or otherwise. If a record cannot show who decided something, then that record cannot be audited.
It doesn't matter how much automated evidence you attach to it.
Right. And if you have a governance system that cannot be audited, you don't actually have a governance system. You just have a very complex, very expensive filing cabinet filled with good intentions.
A filing cabinet with good intentions. That hits incredibly hard for anyone who has ever stared at a Jira board that hasn't been updated in 3 weeks, even though the team is working 60-hour weeks.
Oh, absolutely.
We spend so much organizational energy building workflows and mandatory approval gates. But if the actual authority, the human willing to make a decision, isn't moving through the system is just theater.
The conclusion the author draws is profound. We always assume that execution is the hard part, but in this digital city, execution was never the constraint. The AI bots could execute flawlessly, rapidly, and verify their own work.
The true constraint was deciding.
Making a firm decision and committing it to the record. That is a human limitation, and no amount of AI velocity can solve it.
I think anyone listening right now who works in a massive corporate structure is nodding vigorously. We have all been stuck behind that one approval for 9.5 days, watching the roof catch fire while we wait for a signature.
It is the universal bottleneck.
Okay, as we start to pull all these threads together, let's briefly touch on what happened next, just to close the loop on the timeline. Because the fixes for all this chaos were surprisingly mundane.
Very mundane. The dead server copy was detected and replaced manually that same evening. As soon as a fresh replica spun up, the load balancer had 2 healthy targets, and the system immediately returned to answering requests normally. The 114-second freezes vanished.
But what about the deeper fixes? The unbounded query that caused the memory spike? The missing health checks? Did they just hotfix them in the middle of the night?
No, and this is a crucial mark of maturity. They didn't panic and bypass their own safety protocols. Bounding the reporting tools so we could never ask for everything again, configuring the health checks, adding the request timeouts, those structural changes were written up, tested, and sent through the exact same standard review gates as every other piece of code.
Which is absolutely the correct response. You do not compromise your deployment safety protocols just to fix a safety issue. If you panic and hotfix a broken system, you usually just introduce a secondary, more insidious bug.
Exactly. You respect the pipeline.
So if we look back at the cascade, the 114-second hang, the dead replica hiding in the pool, the read-only audit that crushed the shared memory, the ghost town of governance, it all aggressively points back to our central theme.
It does. When a system embarrasses you, when it freezes, when it crashes under a tiny load, when it exposes its own fragility, your immediate human instinct is to try to make it look better. You want to hide the error trace.
You want to put up a friendly, branded, "we'll be right back" graphic. You want to pretend it was a database anomaly.
But the mature engineering instinct is the exact opposite.
To force the system to tell you more.
Yes. Every single failure we analyze today was a truth-telling failure long before it manifested as a technical crash. The web page couldn't say, "I give up," because nobody gave it a deadline to speak up.
The routing platform couldn't say, "this server is dead," because nobody configured a pulse check.
The board showed lanes as active when nobody had looked at them in a week, because it wasn't forced to record human authority.
The structural fixes aren't massive technological leaps. They are acts of rigorous discipline. Ask for less data. Set strict deadlines on every single network request. Check your own pulse constantly and aggressively. Isolate your heavy workloads from your cognitive layers. And for the love of everything, write down who actually made the decision.
What these fixes buy you isn't necessarily a faster system. What they buy you is a system that can be trusted when it tells you something, especially when the thing it has to tell you is bad news. A system that prefers to look broken rather than lie about being healthy.
Before we wrap up, I want to leave you with a final thought to mull over. Something that builds on the incredible tension we saw between memory and cognition in this architecture. We saw how this highly capable AI fleet digital workers that could write, test, and ship complex code had their ability to think completely suffocated simply because a reporting tool tried to remember everything at once.
Right.
It tried to load the entire history of the city into its active memory, and in doing so, it crashed the system's brain.
It's a very visceral image. Over-remembering, destroying the capacity to act.
It really makes me wonder about our own human systems, our corporate cultures, and even our own minds. We live in an era of functionally infinite data storage. We are heavily incentivized to record every single metric, archive every email thread, log every chat, save every draft.
We hoard data.
We have this profound, almost anxious urge to possess everything, just in case we need to audit it later. But if an artificial intelligence network can be literally paralyzed by the weight of its own unfiltered memory, what does that mean for us? Perhaps the ultimate survival skill moving forward for both digital fleets and human organizations isn't the ability to retain and recall everything.
That's a great point.
Maybe the true mark of intelligence and resilience is the courage to purposefully filter, to aggressively summarize, and to deliberately forget what we do not strictly need right now so that we preserve the space required to actually think.
The strategic advantage of deliberate forgetting. A brilliant way to frame it.
Something to think about the next time you find yourself staring at a spinning loading screen, waiting for a system that doesn't know how to let go. Thank you for joining us on this deep dive. We absolutely love unpacking these complex architectures with you, and we'll catch you on the next one.